Testing sound. Testing sound. All right, seems good. Cool, let's do it. Sweet, so I am back. This is not going to be one of my usual testing sound. Whoa, what's happening now? Testing, mute that. Okay, cool. This is not going to be one of my usual streaming slots, but my kids are being taken care of, and therefore I have a little extra time. And so hopefully I was going to continue with the dev stream that I was doing a couple days ago. So just as an overview, I am working on developing Glyphos, which looks like this. It is it's a VS Code extension, so if you're familiar with VS Code, that's where it lives. So it's just a text editor at the top. I can write whatever I want in here, doesn't matter. But the thing that makes it different is that there's all this stuff over here on the left. And what this is, I won't go through absolutely all of it right now, but there's a type hierarchy that's user defined. It says, okay, everything's an object, ignore joins, everything's an object, but within objects, I've defined a type real, and I've defined a type proposition, so that's like Boolean, and these are like real numbers. And then I've defined a bunch of transformations that you're allowed to do. So for instance, you're allowed to say that x plus 0 is can be mapped to x, where x is real and 0 is 0, which is in turn real. And so that means when if I have a statement like, let's get rid of all this, and say, forget about this for a second. If I say, x plus y plus 0 equals 12, and we hypothesize this, which is just to say we add it as a statement, and we just say, look, it's a statement, trust me. It's a thing that I'm allowed to transform. Then I'd better be able to say that just x plus y is equal to 12, right? Because y plus 0 should certainly be able to transform into x plus y. Indeed, we've derived x plus y equals 12, and here it is. And you can, there's such a thing as the transformation lattice, which could be really simple right now, but it tracks how these things are derived from one another. The transformation lattice is all messed up right now because I've been messing with the force simulation that places the nodes, and I made it worse. But I will be fixing that at some future date. Okay, so, and then the idea, high level, is let's have a way to be able to do math, and by math I don't mean calculations, although we can do those too. Right, 12 plus 5 had better be equal to 17, right? We can do those too, but you can do that in a calculator, you can do that in a spreadsheet. What I think is missing from the desktop and eventually browser ecosystem is a way to do math of the type that you do in, middle school, high school, college, graduate school, if you're an economist or a physicist or a mathematician, an actuary. I used to be an actuary. I wanted to be able to do algebraic manipulations on a computer where I could copy paste, right? And that's immediately makes it a lot easier to do a bunch of complex mathematical operations if I can copy paste. But also where I can't possibly make a mistake, in the sense that if I have the rules defined well and I have the statements defined well, and if I had tried to derive x minus y equals 12 or x plus y equals 0.12, can't do it. Invalid transformation. There's no transformation possible. right? And this is where a lot of errors come from when you're doing math. It's unavoidable. I think my experience taking actual exams was that like I made more of these sorts of errors than the median person. So maybe I have I found one of the easiest exams to be one of the hardest, because all it did over and over again was tested you on your ability to not make off by one mistakes. And I found it really easy to, 5% of the time make it off by one mistake. And those exams are pretty hard. You can't really put a 5% tax on yourself and expect to pass them, although I did by the skin of my teeth. So maybe I'm more motivated than most to want something like this, but I don't want to work through a whole bunch of algebraic calculations where I'm writing and rewriting expressions over and over again just to find out that I flipped the minus sign somewhere, and now I have to carefully and studiously go back through it. That's no fun, and I don't really know why those errors should ever have to happen again in a world of computers. So that's the overall goal. Specifically, what am I working on right now? Again, I'll just go through it very quickly. I talked at quite a length about it last stream. That was mostly a design stream. So here's the goal of Glyphos. This is called Glyphos. The goal is to have it be as fast, if not faster, to do this sort of math. And so obviously, if I have, let's get rid of these statements again. If I have a plus b times c plus d, throw that in the statements. Obviously, I can split that out into something that looks like FOIL. Let me see which version of FOIL we have. This is actually this is a theorem, right? You derive this by distributing. You can see here it says theorem, hypotheses, and the derivation steps that it took to get there. So plus BC plus AD. Okay. Times D. So this would better be true. Can't derive it because parentheses. Oops. Okay, cool. So first off, right there, it's a little kludgy that if I try to just type that in with no parentheses, even when I have somewhere in here as associativity, associativity of addition right here, x plus y plus z is the same thing as x plus y plus z. And the inverse is also true, or the left and the right versions are both true. You'd sort of think that the engine could figure out how to interpret that correctly. But it can't right now because everything has to be very explicit. And I think that explicitness is, gets in the way, especially if, so let's take this and let's look at all of the parentheses. That's what it looks like in all of its parenthetical glory. It's a lot of parentheses. This, if I don't like the order of this, so, we're taught in the US about FOIL first, outside, inside, last. So these two are flipped from the usual way we talk about it. So suppose all I wanted to do was this, flip these two around, you would think I could just derive that because it's so obvious, especially if I didn't have all the parentheses here. It'd be so obvious that, these are equivalent things. It's just associativity lets you forget about parentheses between the sums, and commutativity lets you switch the order. But there's no transformation, and the reason for that is because there's no single transformation that would get you there, and that's kind of a problem. I think it's just ergonomically bad. So what to do about that? Let's switch over to the code. So goal, speed up transformations sufficiently. Ooh, can we redo that? Let's wrap this. Thank you, toast message, please go away. Speed up transformation sufficiently that we can feasibly do multiple transformations in one step. So right now, so to some extent, this is already an impossible goal to achieve because if we look at the app, there can be arbitrarily many statements and arbitrarily many transformations that are being transformed. You can't really have something be, faster than X, right? Say I want this to always happen in 5 seconds. That's the longest I'm willing for a user to wait. That's not going to work. If I can have arbitrarily many inputs that I have to sort through, there's just no way to do that, right? So the best we can do is to say, like, for a certain number of transformations and statements, I need to make this fast enough. And that is actually sufficient because these magnifying glasses over here take stuff in and out of scope. And so what you would do if there were enough statements and transformations that it was problematic is you'd get a timeout message when you tried to do it, and then you'd say, okay, I'll just go and put only the statements and transformations I know are getting transformed in there, and only put those in scope before trying to transform. So let's refine this slightly. Refined goal. Let's just say same thing, but speed up transformation sufficiently that for a small number of statements and transformations, say 3 of each, we can feasibly do multiple transformations in one step. Okay, and maybe you're saying, great, shouldn't that not be very hard? And the answer is it's harder than you would think, for the following reasons. Yeah. I'm not actually sure that the similarity score helps with this goal now that I'm thinking about it. We're still going to do it because it's not hard. Alright, let's say detailed goal for now. Order statements and transformations based on a similarity score so that they're explored in a good order. Something like that. And the similarity score that we're going to use is the following. So something can be transformed if and only if the substatement of the statement is structurally the same, like it's shaped the same as the input of the transform. Thing number 1. Thing number 2 is the substatement is a subtype. So all of the nodes in the substatement are subtypes of the nodes in the input of the transform. That is, the input of the transform is more general than the substatement. So our score is going to be take the max of the following, or the min of the following distance over all substatements, and if walk the substatement and the input, and compute the following if there are nodes on both sides, then if they are commensurate, add 0, else add 1. If nodes are missing on one side or the other, add the number of nodes. So 0 is good. 0 means they're completely commensurate. Adding more than 0 is bad, so we're going to penalize when a node isn't commensurate, and we're going to penalize when nodes are missing. Okay. Let's do it. So here we are. Last time I set up the general way that this is structured, which is within the transformation subclass, or within transformation. Can I turn on? I want to see if I can. I think there's a way to show. Isn't there a way to set up your mouse pointer? Just wanted to see if there's a way to make my mouse pointer a little more obvious. No? Really thought there was a way to like put a circle around it. Yeah. Alright, well, guess not. Really remember that being a thing. Doesn't matter. Okay. I just realized I'm showing the wrong. Am I showing the wrong thing? Yeah. Okay. So let's compute. So we're within the transformation here, and we're basically saying there's a specific case of an algorithmic transformation, which is like when we just compute 5 plus 5 or whatever, and there I'm handling it differently, but within an explicit transformation, we're going to compute the similarity score between the input and get from. Same thing for an output similarity score. We can do a similar thing. And then specific node and general node. Okay, so how's this going to work? We're going to say so we need to recurse. So if specific, let's see here, specific node dot get and children is greater than general node get and children. We can just do it different then. So if they're not equal, then we know they don't match. Do do we care about comparing those that do match? Maybe. Okay, fine. For I in all right, let's say let's specific node and children. Let's just say max or shared children. Max is going to be specific node.get and children. Dot max general no dot min general node dot get and children. So this is the number of children that could be shared. For I and 0 shared children max, we'll say let's let mute to return 0 to return plus equals self.compute similarity score hierarchy specific node.get child fine children I specific node it's not gonna like this because I think the bar checker's not gonna like this, but we'll sort that out in a moment because it's not gonna like that we're pulling values out of a reference. Okay, so for the ones that are shared, we recurse and get their similarity scores. And then if there's a difference, we need that too. So so like for let's see here, let's call this n shared children. And then let n missing children be, it's going to be the same thing. But we're going to max it out. And then we'll say for j in n shared children, let's just do it this way. And shared children through specific node.get and children. return plus equals specific node get children j. Really, it could be I. Ooh. What I was trying to do. Dot get. Length symbols. What do I want to call this? What I want is the number of nodes. Get size. Size seems unambiguous. And here we'll do the same thing. Okay. And so that is the recursive case, and then we need if specific node. Actually, we need hierarchy. So the base case is going to be the hierarchy. Is subtype of specific node dot get evaluates the type, and same thing here. Channel node. Okay. Then to return plus equals 0, else to return plus equals 1, to return. And obviously this doesn't actually have to happen. Do nothing. They're commensurate. Okay, so this can fail. Not worried about it failing silently for the heuristic. Okay. So let's just go through this. So the recursion is look at all the shared children and recurse. The general node is where we go through it. And then this is why we go through it. Wow. Chris. Okay. So the recursion is we go through the shared nodes, we compute their similarity scores, and we add them to whatever we're doing. For anything that's missing, we add the size of what remains. This won't be a problem because one of these two is going to be trivial, which is fine. Get size will just go implement, which is also fine. I really feel like I've implemented that before. And then this is the case for current node. Recurse over shared nodes. Penalize for missing nodes on one side or the other. Okay. And this will work in the n shared children equals 0 case. Yes. Okay. Let's go check on get size. What is this? Okay. SymbolNode. Length. Length. That makes sense. Okay. It's like maybe more ambiguous, but it's fine. All right. So what's going on here? Oops. Expected use and found use size. Sure, fine. I don't know. Should the penalty just be in terms of use size? I don't think it matters tremendously. Let's just do it like that. And then there's some constant somewhere also. I thought, is there not? Why do I really feel like there should be a constant there? Didn't I have some constant? No, maybe not. Okay. Bunch of errors because of something that is out of my control that don't actually matter. Okay, let's run tests, make sure everything compiles. It's almost certainly worth writing a test for this. It's usually worth writing a test. Probably would also be good if the code compiled. Mismatch types. Sure. Get symbol. Okay, the point is that get symbol can return an error, which I'm mapping. Seems fine. Unwrap or. I always do that because I never use unwrap usually. Can't compare. Can't compare a what with a what? Symbol with a symbol. But I can compare references, can I not? Okay, I really feel like the, yeah, what is this? Max similarity score, right, I don't need that anymore. I really feel like the bar checker should be yelling at me for pulling, there we go, oh, nope. Did have this. Oh, right. Yeah, I do want that. Where did my max similarity score go? I like remember putting that in. That makes me a little nervous. Okay. I'm in the right branch, right? Yeah, I am. Presumably something went wrong when I let it stomp on my file. I thought it said it had been, my local copy was, yeah, it's weird. I'm not sure about that one. What is this? Oh, sure. Okay, looks like we're gonna compile, even though really the bird checker doesn't have a problem. I'm surprised. Let's just think about this. So get children returns a reference to a vector. Huh. I guess somehow the bird checker must be okay with it because I am just borrowing the contents of something that's borrowed. That seems usually not allowed. I feel like there's some sneakiness going on there, but I'm not going to worry about it. Okay. Let's write a test. Where's a sane test? Where's a sane place for my test to go? Somewhere above this. Let's take this as a starting point. I'm of the perhaps wrong opinion that in your tests it's okay to copy and paste a bunch of code around. I've seen people put lots of setup and teardown functions in, and I'm not sure that it follows the same pattern that production code does in reality. Okay, let's put it here. And we're going to say test transformation, compute similarity score, commutativity, and some statement about commutativity, sure. And then, let's see here. So commutativity is just saying A equals B is going to B equals A. Could be called symmetry also. And the statement is saying A equals B equals C. Fine, this seems like a reasonable thing to test. And so we want transformation, compute similarity, score. Ooh, we need a type hierarchy. Do we have that here? Don't. Okay. We can do something like this. Let's call it hierarchy. And let's say equals is Boolean, don't care. And sure, int is fine. Let's add real. And let's add int. And let's say that the symbol node should be how does this work? Symbol new a integer. something here. So b integer. Okay, and then this will be the same, except it will be B and A. Oh, this is the rule. Let's make these. It needs a dot into. Okay, fine. Let's make these real dot into. Okay. Fair enough. And then the statement should be this. And this. And then we'll compute the similarity score using hierarchy, statement, and transformation, because the statement is the specific thing, the transformation is the general thing. Yep, that's true. And and what do we believe that should work out to? So equals, it should just be 0, right? Because they match. Like they are applicable. What's this? Statement. Oh, commutativity. I mean, sure. Okay. Could not compile. Oh, right. Get from. Okay, failed. 4 does not equal 0. That's true. 4 does not equal 0. Oh, this shouldn't be a leaf object. This should be. Can I fix that? I can fix that. Should be this. I don't think this is the issue though. equals 3. Somehow that made it better. Oh yeah, it sort of should make it better. I get it. Okay. The problem, I was thinking this would be 0 because this gets minned over, but I'm calling compute similarity score directly, which doesn't get minned over. So what should it be? So it should look at both the from and this. It should say, okay, it's equal, so those are commensurate. That gets a 0. On the left, it's going to have some score. On the right, it's going to have some other score, which should be equal. So on the right, it's going to get a 0. So then it comes down to just how it scores this versus a single node. And it should say the types are different. And one of them has 2 children, so that's going to be 3. So that's correct. But it should then be the case that if we say commutativity dot into, just say commutativity, it's here. Let commutativity transform equal commutativity dot into. Let's be explicit that this is a transform. And then it's dot similarity, get input similarity score with statement. And now this should be 0. That's a 9. Because this should actually take the max, or the min. Still fails. Okay. So why not? Compute similarity score. Is there no min actually being taken anywhere? Yeah, there's no min actually being taken anywhere. That's why. So what we want is like compute min similarity score. Okay. Compute substatement similarity score. This is going to be different between the two, though, actually. So what if we just do this also feels like it's going to benefit from memoization, but for substatement in input.get substatements. Let's do it this way, actually. Let's do it as input.get substatements into iter map substatement, and then let's do this. Ugh. Doesn't like it because it's not block mode. And we need a unwrap or this is just expect statements always have at least one substatement. Okay. Unused variable substatement. That is not intentional. Substatement. And this can just be iter. And then we're going to do a equivalent thing, but backwards down here. So we're going to go output. And here it's going to be t.get2. And here it's going to be substatement. And there we're going to close the parens and close this. Miss a paren somewhere. Okay. All right, let's see if that's better. Let's just run this one test. I hid my coffee at the back of my desk. Amazing. I love discovering that I still have more coffee. It's a very nice feeling. And it passed. Sweet. Okay, that worked. Cool. So that's pretty comforting. Let's switch all of these to integers. It should still work. Integer. That doesn't change the first computation, does it? No, it shouldn't. Okay, we should already have a benchmark set up, so we should just be able to go to, okay, so let's add this to get, test the similarity score. I didn't really test the output one. sort of matters. I think it's fine though. Okay. Let's go transform into. Transform. Okay, so here's where we go through the list. So we have our desired statement, which is the output. We have our instantiated transforms, which are the transforms we're going to walk through, and we have our candidate statements. So what we want to do is say let mute ordered instantiated transformations equals transformation instantiated, I can spell, it's fine, transformations into iter collect, and we're going to collect these as vectors, and then we're going to say instantiated transformations dot sort by sort unstable should be fine. And here it's, how does this work? What's the comparator function? Takes two things and compares them with partial compare. Okay. A, B. So in here, let's go map transformation, and then it's going to be T, comma, T dot similarity, in output similarity score, desired. Okay, and then we can say A.1 dot partial compare B.1. Okay, so what's that going to do? It's going to take the instantiated transforms, it's going to compute the output similarity score, and for tuple. Why is that a tuple? Oh, sure. T blank is what we care about, but then we need it to be T, so it's not T, arbitrary. Arbitrary, and then this is going to be 2, and 2, and then the score no longer matters, score. And should be okay. What's wrong? No 2 on this type, but there are 3 things in this type. Ordered instantiated transformations, and then again over here, ordered instantiated transformations. Okay, and then we're going to do the same thing with the statements. This time it'll be an input similarity. There's a bit of a catch. Is there a bit of a catch? Does this work again? No, there's no catch. Okay. Ah, right. It puts joins together. That's fine. Okay. Statements. Let mute ordered statements be statements dot into iter dot map s, and then we will go instantiated transform dot get input similarity score s, no, hierarchy s dot collect vec, and then we're gonna add one more paren here, and not the best use of dim I've ever done. And then wait, what's happening? And the thing, and then ordered statements dot sort by unstable by a b a dot one dot partial pair b dot one needs to be a reference, and then this is in ordered statements. Okay. Hierarchy. Okay. Cargo test. Oh. No method named outputs similarity score. What's the problem? Oh, Rust can't find value hierarchy. Really? Oh, it's called types. Alright, fine. Types. Oops. I guess that's more explicit. Probably is if you don't know what you're looking at already. Okay. Could not compile. Oh, it's an available transform. I forget what an available transform is. Right, I can just throw a get transformation. Blah. There we go. And same thing over here somewhere. Wait, not there. Here. Okay. And then this is statement and the score that we don't care about anymore. Okay. What's the problem? Expected ordering. Oh, it has to be an ordering. Mute, compare, returns and ordering. Okay. So just .cmp is fine. I don't know why they abbreviate these things. I don't like that it's .cmp. This feels bad. Okay. And then what's going on? Expected. Okay. Fair enough. Borrow something I'm not allowed to borrow. Borrow moved value S. I mean, I'd rather not clone it. If I do this, and then I do score, that's okay because it comes out of scope. Okay, fair enough. Do I have to do the same thing over here? Yep. Okay. I see. Yeah, okay, that's sensible. Okay. Hey, our code's compiling. That's nice. It'd be nice if all the tests passed too. Will they? Probably. The real question is going to be how the benchmarks perform. So for the benchmarks, where are they? They're here. So I just have a couple of tests set up that do a bunch of manipulation. They take some time because it's kind of slow. So, okay, all of our tests passed. Let's see how our benchmarks do. Now, I haven't actually run the benchmarks in a while, so it's not like impossible that I've done something else that affects the speed, which is too bad. Maybe I should have run the benchmarks on main. I don't think so, though. I haven't really been touching this stuff very much. I think it should be okay. So hopefully we get a speed up. The goal isn't necessarily to have a huge speed up here, so much as we need a similarity score when we're trying to do multiple transforms in a row. Because we're going to want to say, we're going to want to come up with a chain of potential transforms to do. But let's see how we do here, because this shouldn't be super slow. Like, we're doing it a few times. It's not great. I don't love it. One thing that's separate that I've been thinking about is whether, so right now we sort of do this naively in terms of, like, the data structures are all pretty object oriented. So a statement is a symbol node. It's a big oh, interesting. I missed a... I used to just have this called the symbolic manipulation engine, and then I made a name for it. It's a good thing I didn't name it my address or something. My social security number. Okay. Oh. Huh. I wonder why it's still building. Waiting for other jobs to finish. Seems like the sort of thing that could never finish. Let's just kill it. So right now we are pretty naive about how we store symbol nodes and how we store transformations. So they're like big nested tree structures, right? They're Rust structs. And Rust is really good at abstraction from a speed perspective, but not perfect. Nobody is. And so I've been thinking about, like, when you do chess computing, for instance, something that I have a little bit of experience with, and I had this really eye-opening experience with where I started writing, not a chess engine, but something I was using for chess, and I just did it naively with Rust structs. And then at some point I switched it over to bitboards, which is where you set up the board as a series of bitboards. So there will be one for each type of piece. So there will be one for the white knights, for instance, and that'll be stored as a number that's just a 64-bit grid, 8x8 grid, but that 8x8 grid is just a number. You just read it off, and it's ones and zeros that tell you where the knights are and where they're not. And so you put together, where the knights are, where the bishops, and so on and so forth. And it speeds everything up dramatically because you're using binary numbers, like you're using core types within, as the primitives for the chess engine. And so I've been trying to think about how to do something similar here. And the thing I keep running into is, like, the reason it works so well with chess is, like, yes, you're using core primitives, but also the chess moves are expressible in those core primitives. So, like, when a knight moves, you don't have to go touch the whole, you don't have to touch 6 different bitboards. You just touch the one for knights. And so, all you do is you go find the right bitboard, and then you apply a transformation to that, binary string, which is really fast. Also, chessboards are a known size. These things are not true of the symbol nodes. Sorry, I'm watching this benchmark thing happen, and in the back of my mind I'm thinking this is not a good benchmark, because I'm also streaming, which is probably eating up my CPU. But we'll see what it thinks. So anyway, yeah, thinking about a better representation of symbol nodes that might be good. And the other things, so, like, just, can I use this while it's running? Yeah, I can. So, like, better representation of symbol nodes. Question. Can we use some sort of binary strings And a naive answer is yes for each type. Use 1 to store the structure using balanced parens, and then use 1 for each type in the, or 1 for each label, and keep a map of label to symbol. So that would be something like if you had, you know, A equals B, then you would have structure, and A equals B looks like this, and so you'd have this maps to like 1 1 0 1 0 1 0 1 1 or something, and then for A you'd have 0 0 1 0 0 0 0 0 0. For equals you'd have 0 0 0 0 1 0 0 0 0, and so on. The trouble with doing that is transformations aren't really encoded like this. So like if we're doing a transformation on this, we're going to end up needing to touch we're going to have to, we need to be able to answer subtype questions, which maybe is okay. Which might be okay, since if we want to know whether one thing is a subtype of another, we can walk the hierarchy, the type hierarchy, and union together the structure. But the other thing is we need to know about substructure. So also need to be able to compute substructure. But actually that's not bad either. We can do by taking substrings across everything. Maybe this is not bad actually. So just I'm thinking out loud, which I imagine is not incredibly clear. So let's say we have a symbol node like this, and we want to break it down into bit strings that encode what's going on. Now, we don't know what size those bit strings are going to fit into, which is a bit of a problem. But okay, suppose we work around that. Which we might not be able to do, because I don't think 64 is a particularly big number. Also, by the way, check out how slow my benchmarks are going. I like how somehow it's found outliers. I don't know how you can find outliers while you're still running the benchmark, but whatever. So we encode the structure based on where the parentheses are. And we have the same length bit strings for each label. And so for each symbol node, we end up carrying around well, somewhere there's going to be the type hierarchy, but also there's going to be a map from the label to the symbol, which technically is not a constraint I currently have on symbol nodes, but I think it's a fine one. Like, I think things are going to get pretty confusing if you start saying that A is both a real number and like, it should be unambiguous. So we're going to carry around a map from the label to the symbol, and then we're going to have a string for each label and a string for the structure, a byte string, a bit string, whatever, a binary number for the structure and a binary number for each label. And then if we want to get a sub tree, a subset, all we do is walk some number of parentheses in, and then take the substring until we get some number of parentheses out, and do the same thing across each of the labels, which I imagine is quite fast, assuming that the byte string, that the binary numbers can be whatever size, which in practice they can't be bigger than 64. And if we want to know the subtype, then what do? We have we're asking some question like, 2 equals 5 is subtype of A equals B, question mark. Then we would well, one thing we could do is just walk each string and check subtypes. Which is like fine. Benchmarks still haven't finished. I'm gonna get, oh, they have finished. They had finished, it just didn't show me anything. Okay. Found 7 outliers, sure. Where's my, oh, I don't have a reference point, because I moved this repo and the benchmarks don't stick around. So now I really don't know. Let me look and see if I can find those. I moved this repo and this is in my git ignore, so I'm just checking in the background what the bench is probably. No. Where's the output? Where's the output of this go? Where does the output of the benchmarks go? Benchmarking, blah, blah, blah. What's this thing called? Criterion. Rust. Debugging output. HTML report, target criterion report. Oh, got it. Okay, so target criterion, really? Yeah, alright, so I guess I just don't have any benchmarks. So I can't tell if this made it faster or not. I can remove it. Okay, let's do this. Let's say get at all, get use similarity score to sort transformations and statements before processing. By the way, I'm sorting in the right direction, right? I'm sorting increasing. Yeah, which means it's going to do the good ones first. Okay. Get push. And now what happens if I go get checkout main, get pull origin main, hard bench. So now it should run the unchanged version. And I think it should still give me a benchmark, but at least I can check. At least this way, after I push, or after I do a pull request, I should be able to rerun it and get an answer. Okay, so while that runs, do I want to do this? I sort of like it. It's gonna get messy. It's not gonna get messy. It's gonna be a deep refactor. But I have good tests. And I do think some things are gonna get a lot faster if we do this. I'm gonna be annoyed if they don't. If I go through this whole thing and then it's like, 3% faster. Ugh. Oh shoot. Okay, let's just edit it and YOLO it to main. I'm kind of excited for this binary optimization. I think it could be powerful. Oh, this looks like it's faster, just based on the estimate. But we'll see. 47 seconds. I'm gonna get a water. We'll be back. Okay, so interestingly, performance has improved over that's probably over the run we just did. Yeah. Okay. Alright, well, let's YOLO this to main. Which is needed renaming. Yeah, main. And then check out similarity heuristic. Whoops. Don't need the B. Get poll origin main. Don't make me do. Nice. Okay. And now get status. Cool. And I'm just going to pull request this quickly and why, but for some reason on my GitHub it stopped doing the thing where it asks you to create a pull request automatically. Like it says you've committed code, you know, you've had commits within the last 5 minutes or whatever. Would you like to create a pull request? And I thought that was a pretty useful feature, so I don't know whether they got rid of it or whether somehow my repo settings changed, but a little sad that it no longer exists. Okay, I'm just gonna scan through what I've done. Looks good. And go ahead and merge. I know you can't see this, but it's not very interesting anyway. Okay. And now we check out main get pull. Whoops. That's not where I want to do that. Get check out main get pull origin main. Test. And we'll cargo test and cargo bench, and I'm expecting it to go up, but that's sort of okay because we need our similarity score anyway. And maybe we just remove the sort that we just did until later. But I think for now I'm going to leave it as is. And I think we're going to work on this binary change. I wonder if ChatGPT has an opinion. Let's just see what it thinks. Manipulating symbols. E.g. transformations like A plus B plus A, or A minus A, 0. Can be defined and then can be applied to statements in scope. X plus y minus x to yield x minus x plus y, and subsequently 0 plus y, etc. It's very general, but internally represents the statements as trees of symbols which have labels and types. I'm trying to optimize it. Let's cargo bench over here. Cargo bench. And thinking about representing the symbol trees instead using binary strings, where for each tree I keep track of a map from label to symbol, which includes type. A binary string encoding its structure, e.g. a plus b would go to one one zero one zero one zero one one. A binary string, well, a binary encoding. Coding for each label indicating where it is, e.g. for A in the example above, it would be 0, 0, 1, 0, 0, 0, 0, 0, 0. It feels like this would allow me to look at substrings by just subtrees, by just filtering down, by just taking substrings between parentheses across the different encodings. And I could look at types, relationships by comparing encodings for different labels corresponding to different types in the type hierarchy, e.g. combine all strings for all integers and then see if it's a and then for it with the one for all reals to determine if it's a subset or not. Would you imagine this to make things faster as opposed to having a Rust struct of like symbol node symbol children vec symbol node. Alright, let's see what ChatGPT thinks about this. I know you can't see it. Sorry about that. Don't have a great way to show it. Could offer some performance benefits. Efficient subtree operations. Reduce the memory footprint. fast serialization and deserialization. I think I actually don't want to serialize and deserialize these things. That's sort of an interesting point. I guess it's fine. Simplified type checks. Okay. It's gonna add complexity and readability. Yeah, sure. Performance overheads. While certain operations might be faster, the overhead of managing binary strings, such as updating them when tree structure changes, could offset some of the performance gains. Adding or removing nodes. Flexibility. And then it's like, yeah, go benchmark this. Sure. Obviously, that is what I'm going to do. Okay. I'm gonna try 03 and just see if it has anything else interesting to say. This model thinks that it'll be faster if my workload involves many read-only queries where you leverage bit-level operations and your trees are large enough that memory locality becomes a dominating factor. Profile my app first. Measure where my bottlenecks lie. Yeah, that's fair. Final thought. Unless you have concrete evidence from profiling that that's where the bottleneck is, the complexity won't be worth it. Sure. Okay, I agree. I guess performance has regressed. Yeah, I'm not surprised. Okay, let's do a couple things. First off, let's just revert this to get our performance back. Commits. Let's go back to the benches. Let's go to how do I commits? I don't want to revert this. I want house files at this point in the history. There we go. Okay. Source transformations. to do is transform into. Oh, that's false. Ugh. GitHub, why are you so slow? Why are you so slow, GitHub? Where's my code search? Open symbols panel. There we go. Try transform into. Not this one. That one. Yeah, this one. Okay. Let's go. Try transform into. Oops. It's this one, yeah? No, it's the other one. This one? Yep. Okay, replace it with this. And nuke all of this. Diff. Just that. Okay, so I guess the question is how would I convince myself that the binary encoding is going to help? And my intuition from the chess example is that it will. Let's think about what it would actually take, I guess. So basically, I think what we'd want to do is have some kind of like fast symbol node, because it's still nice to have the tree representation like during parsing. So we want to parse it out as a symbol node and then pipe it into something faster. And the something faster, like all these instantiations could still come from the tree version. Length would be easy to compute. The length becomes just the sum over, yeah, so that's fast. Arbitrary nodes. Yeah, that's okay, because that would be, I guess the map would go from labels to arbitrary node, or to symbol node roots, which is fine. So contains a substatement just becomes sort of a substatement query across all the strings. So you would just, for each string in the substatement, you would check if it was the same substring of the main statement. That's fine. That's going to be a lot faster than this. Get substatements is easy. You just walk over the parentheses and pull out the substrings. Get predicates. This is fine. This mostly just doesn't change. Get arbitrary nodes. Should be mostly fine. Is arbitrary is fine. Is join is fine. This is all good. Get depth. Yeah, we could do this recursively. We could also... No, that's faster. That gets a lot faster. Get children. I'm gonna run to the bathroom quickly. Okay. So let's keep going through. So has children. So push child. So that one's going to be slower. It's like not tremendously obvious how often this is going to happen, though. With child replaced. Get root. Get symbol. Split delimiters. What is split delimiters? Split if delimiter. Oh, got it. Fine. Split self. Split. SymbolNode address. So these are kind of interesting. So a SymbolNode address tells you how to walk the tree. And so it'll be like a series of indices. Shouldn't be bad though. Replace by name. Like these replacements are a little bit, those are going to be pretty iffy. So that's one thing that's worth recognizing. Oh, we got no change in performance. Well, that's a bit surprising. And no outliers. Okay, so maybe it doesn't matter that much and maybe I should leave it in. Let's think about this binary case. So replace all. Yeah, like these replacements are gonna be a little dicey. Find should get faster. I'm not sure whether SymbolNode address is what I want to use anymore. We might want to update SymbolNode address to be something else. Yeah, no change in performance. Okay. Let's undo this then. To interpreted string, I mean, some of these recursive things are pretty nice. But okay, I mean, some of these things we can just pipe it back into a SymbolNode, right? And the other thing is, we can do all of this with a new type, I think, so that we're not risking very much. I mean, we can roll stuff back, but also we can use it in kind of a targeted way. We might not have to rewrite all of these. Okay, I think I want to do this. it's work, but like I don't think it's too bad. Internal binary representation of SymbolNode trees. Let's do it. Check out binary symbol nodes. All right, let's see what we can do. And the other nice thing about this is that writing tests isn't going to be too bad, because we can write tests that just do the same thing on both the binary version and the SymbolNode version, and then swap amongst themselves. So let's see here. SymbolNode error. Predicate. Let's go to SymbolNode. We want all this. I think we want all this. I kind of hate how I did debug anyway, so we won't take that. So let's go binary SymbolNode. It's going to have let's just call this symbols or nodes. Let's call it nodes. Binary SymbolNode. Is that what I want to call it? Yeah, for now. Binary symbol tree. Binary statement. Oh, binary symbol tree. Okay. And this will be a hash map from labels, which are strings. SymbolNode. Something. Label. Do I have a name for those anyway? Anywhere? Root. Can I get a definition? SymbolNode root. Symbol. Where's my definition of symbol? Is my definition of symbol? Symbol name is what I use for it. Symbol name goes to a SymbolNode root. And then we have structure, which is for now going to be a U64, I think. So I think if I use a U size, it's still going to be a problem. Something called a big int. Bitvec. Seems like Bitvec is going to be my best bet. Okay, so let's say Bitvec. I assume it's like this, but let's go cargo add Bitvec. And rust. Just looking at how we use Bitvec prelude, bits. Just reading about Bitvec and trying to figure out if this is what I want to use. I'd like something. Uses of Bitvec generally fall into compact and fast uses. Get started, you can perform basic stuff, blah blah blah, bool n, back n. This looks okay, but not great. I don't want to use byte buffers. Don't really want to use a custom struct. But if I use larger integers, I'm going to have a problem. Bitvec. How do I know what type that is? I need it to be owned. Oh, it is a Bitvec type. Okay. All right, let's just see how this works. Use Bitvec prelude. Like that. And then we'll see what happens. And then node trees. And this will be a hash map from symbol name to Bitvec. Oh god, it can't be deserialized. Really? also I'm going to need to implement my own hash. This seems like a problem though. It says it's Saturday. Bitback version is this. Features Saturday. Now though, maybe. Okay. All right. Cool. And then we'll have to implement our own hash, which is not a big deal. And we'll have to implement. Okay, from SymbolNode root for. Oh, did I already? Yeah, I did. Okay. From SymbolNode root for binary symbol tree. And we're gonna say. Let nodes be vec root dot get name root dot clone no root into iter dot collect nodes structure and you know, rather than doing this manually here, because this isn't important that it's fast, I think what we'll do is we'll do SymbolNode from value.into, and then we'll impl from SymbolNode for binary symbol tree. And then this one is going to be the tricky one, but let's just to do it for now. From symbol for binary symbol tree, and it's going to be the same thing as this. For now. Why doesn't to do work? Impl. Oh, I'm missing. symbol node self to do. Symbol node root. Okay. Those are updated. Okay, we're still getting the deserializer, which we're always going to get. Let's keep going. I don't want to impl debug yet. Okay, do I want to just take every single function here? Not yet. Let's start by just implementing new pubstruct symbol node. Actually, let's we're gonna have to impl these things. Partial ord and the ord. Impl partial ord for binary symbol tree. And this is going to be self.cmp other, but then full ord is going to be something we do later. Okay, and let's, wait, why? Partial ord is not implemented. Oh, right. Okay. And now let's create a new function. I would like it to be below all this stuff. Okay, and then, all right, and then let's think of how we want to convert between these two things. In fact, let's write a test. Test binary symbol tree instantiate from, we'll just say from symbol node. Why is it expecting a bang? It's not. Okay, so let's node equals symbol node leaf object whatever 5. Let expected be binary symbol tree new. Nodes. Let expected nodes be .toString goes to node.get root. Nodes structure and node trees. And so structure is going to be bitback 101. Is this how we do balance parens? I don't like this. Okay, I'm happy with that. Just asking ChatGPT what it thought about my structure. Let expected trees be back 5.toString. Bitback 010. Okay, and then this is expected nodes, expected structure, and expected trees. Node expected node.into. Okay. Doesn't implement debug. Okay, for now, simple tree debug. I assume this is not going to compile for some reason that I haven't thought of yet. And it's gonna die. It should die here, which is fine. Oh yeah, here we go. Yeah, fair. Ugh. I'd love to get rid of all of these noisy errors that aren't really errors, but I looked into it. And it doesn't seem possible. Okay. So, how are we actually implementing this? Not this, sorry. This. Wait, really? Against this function are incorrect. That's fair. Type annotations necessary. Really? Okay. Do I have to tell you what type this is? Seems like I should not, but maybe because it's a macro. So this is a binary symbol tree. Running out of steam a little bit. Feel it. Ran out of coffee too. Wait, did I? Yeah, I ran out of coffee too. Bummer. Okay. No errors. Okay, so how are we going to convert this? So, there's another issue, which is that we need symbol name to be unique now. Which is fine. I think we should enforce that anyway. But if we enforce it by panicking, that's going to blow everything up. And if we don't enforce it by panicking, then we need an error to propagate. And if we need an error to propagate, then this can't just be a from. So I guess for now, or we could have it fail silently. Which I sort of hate. I think for now, let's have it panic. Okay, so let nodes be, let's call this symbol node dot get nodes roots. Get root name map. Get roots by name. Expect roots should be root names should be unique. And let's say to do figure out if we need to handle this assertion more gracefully. Okay. Problem for future Chris. Let's say let structure be Self get let's see here. Do structure and trees at the same time. And trees, SymbolNode, and then self new node structure trees. Sensible. Okay, get root. Let's go pub function. Let's make it not public, I think. Get roots by name. It will return a hash map of SymbolNode name, or just symbol name, right? To SymbolNode root. And the way it will do this is it will say, let's meet to return be self.getChildren .map child dot get root by name collect flatten collect, and then to return is to return dot into iter dot union self dot get name back of this to get root into iter collect as a hash map cloned collect, and then we return that. Okay. Let's get roots by name, get children, just iter should be fine. Type annotations needed, hash map, blank. Nothing found for unions, just this, right? No method union for hash map. Extend. Extend modifies its receiver in place. Okay. To return dot extend, it's modified in place, so then we have to return to return. And just like that. Mismatch type. Expected string bound SymbolNode root. We need this. Type mismatch. Self get root. Get roots by name. get root.clone. Okie doke, get roots by name, that works. And then we need the other function, get structure and trees. Get structure and trees. SymbolNode. SymbolNode. And here we want a bitback and a hash map from symbol name to a bitback. Okay. All right, and so here, what to do? Let mute to return. Equals bitback new. This isn't quite gonna work. We also need to know let's see here, it's gonna be better if we know the nodes as well. So like nodes, hash map, symbol name, symbol node root. And then we're going to say structure. We'll always start with a 1. And let mute node trees. There's going to be nodes dot iter dot map. Doesn't it does matter. Name root name bitback 0 dot collect. Okay, and then let's get the children first. So let children structures children structures and trees will be will be SymbolNode dot get children dot map child trees, nodes, child, don't collect. It occurs to me that this can be a reference. Can make things easier. Okay. And this way, the structure is going to be bitback. There's always going to be a 0. So the structure is if children structures and trees dot length is greater than 0, then it's going to be one thing. Otherwise, it's going to be It can just be 2 return, and this never needs to be mutable, I think. Return 2 return at the end of this. So if we have any children, if we don't have children, that's the easier case, then it's going to be 1, 0, 1. Let the structure be this, and so then node trees is going to be this. Name bitback 1 no, 0 0 and or I guess we can do it as false, false, and then SymbolNode dot get name equals name. And then structure node trees. And here we do something similar, except that it's 0. There are 2 more sets of parentheses, and then children structure. So it's going to be children structure. This, I think, structure equals like this, and then we'll figure that out in a moment. All right, what's going on? So a couple things. One, is this actually how we do bitvec operations? Push and extend. Can I not use bit operations on it? Okay, so it's going to be okay, so in principle I can extend this structure dot extend children structure dot extend bitvec. Okay, these aren't going to be the right types. We'll figure it out. Missing that semicolon. Okay. So children structure should be easy-ish. We just want to go children. The children structure, children trees, the children structure and trees dot into iter dot map. Structure trees. This needs to be a fold or a reduce. Which means I need something like this. Accumulated S, accumulated T's, and then S accumulated dot extend S. And T's accumulated. Ooh, this is sort of a pain. Okay, let's not do this as a fold. Let's do it as view children structures. Back new, let mute children. children trees be a hash map new for STS in children structures and trees. Children structures dot extend s. For children, tree is always guaranteed to exist. No, they're not. So for label encoding in T's children trees dot entry label dot. I always forget how to do this. Entry or default, and then we push. Is it or default? Yes, it is. Entry or default. Push. Encoding. Okay. And then node trees. How do we want to do this? Isn't it? Okay, I don't think that's what we want. Children trees dot into header. Not actually. right in here, we want let's open something up. And we're going to say let mute do I already have something called encoding? No. Encoding equals bitback of false symbol node.get name. And then at the end, we're going to do encoding.push false to close the parenthesis. And then in the middle, we're going to have if children trees, or maybe even just match children trees dot get name some tree, then encoding dot extend tree. Otherwise, don't do anything. Okay. So get children.map. Okay, so we apply mismatch type expected symbol node. Am I cloning this every time? I don't think I can intuiter this. I guess I'm cloning this every time. Let's just make sure. So this should be a hash map of something to something. No, it should be a vector of something. Yeah. Okay, children trees is going to be a hash map. Can't invert the type of the value. Fine. It's going to be a bitback. Okay. default extend encoding. Yeah, because we're just concatenating together the encoding. Let's match comparison operators. Comparison operators can't be chained. So name is a name. I'm not chaining anything. SymbolNode.getName should be a thing, right? SymbolNode root. I think I need to do like get name string, get root as string, or get root dot get name. Is that a thing? I'm not comparing comparison operators. Why does it think I am? Use a non-constant value and a constant non-constant value. What? Encoded bit be this. Encoded bit. Maybe this has to be a constant. Encoding push. Okay. Can't compare. Expected bool found integer. This one is false and integer. Okay, that works. So I assume it's a similar story here. Okay. Expected bool found integer. Why? I mean, I can push false on here. Okay, that's consistent with what I did above. And then hash map of stringed bitvac cannot be built over iterators of type. That string, we've got some. So I guess we'll dot clone this. And dot clone this. Get reads by name. Needs to return a result. Okay, so it's actually not obvious where this should happen. So I think for now I'm going to get rid of this, and I'm going to get rid of the expect. And I'm going to make a note for myself to make sure that symbols don't share labels while having different types. And we're just going to put that on the app to do, and trees, these nodes. Alright, so in theory this compiles, and the test should pass. Can't compile. Alright. I would love to hear from anybody who knows how to jump out of the terminal in NVim without using the mouse. Like, not jump out of the terminal, but go from insert mode to not insert mode. Because that's the thing I don't know how to do. What's happening here? SymbolNode. Why aren't we passing that in as a reference? I think it should be. Saves me some cloning. That was the problem here. Bitvac. say this. Trying to figure out what type this needs to be. Okay, what happens if I say bit back here and then get an error back? Alright. What happens if I say bool? Construct bit back. Okay. What if I say bit back bool? Not helping. Let's see if ChatGPT knows. Because I can't tell from the documentation. Okay, so the first generic is bit order, most significant bit first, least significant bit first. I would like the one that I can read. Okay. Sure, let's do that. So LSB0 and U8. U64. What's happening? Goes the other way. Goes the other way. Or this usize for now. Okay. Okay, and I guess usize is probably good because it's the size that the operating system likes, usually, I think. Encoding is mutable. Okay, let's try this again. I'm wondering if it's going to make sense to pull some of these operations out. Like this bit is gonna kind of just be what it looks like to add a new node. Alright, we're gonna try to get this to pass and then we'll call it a stream. Let's see if this passes. We should have just run the test itself. Ooh, passed. Wow. Okay, let's try another one then. Let's go find like equals B. And do we want to just do it this way? Sure. Parser equals B. Expected node is going to be equals this and bucket root. Okay. And then expected structure is going to be 1, 0, 1, 0, 0, 1, 1, right? Because we're going to open a paren, we're going to have equals, open a paren, we're going to have A, we're going to have A, close paren, close paren. It's balanced. And the expected trees are going to be two of them. So the equals one is going to go 0, 0, no, 0, 1, 0, 0, 0, 0, 0. And this one's going to be 0, 0, 0, 1, 1, 0, 0. Okay. And then this is going to be A equals A done into. Yes. Expected function. Expected function, really? There we go. And let's just run this test. Ooh. Borrowed mood value. A equals a clone. A equals okay. And then cargo test binary symbol tree. Kind of expecting this to break. Kinda, sorta, maybe. Super backlit. I have to do something about my camera setup, I think. If I go over here, am I less backlit? Yeah. Okay. Failed. This is gonna matter, but so what's going on here? Left versus right. Equals integer a. Sure, that seems fine. Let's just pull the nodes out. Let's pull structure out. And let's pull node trees out. Let's pull nodes out. Let's pull structure out, and let's pull. There's trees. There's trees out. Okay, the bits are really different. So, actual. So left is the actual. What is happening? Where's my thing I just dumped out here? Okay, so actual has 11 bits. So it should be a equals a, which is equals a, which is 0, 1 0 1 0 0 1 1 1 0 1 0 0 1 1. what we get over there. So the expected is what I expect. The actual, we're getting 101. We're getting an extra layer of parentheses that we don't want. Which we're getting because we're surrounding it with an extra bit of parentheses. So we can just say let encoding equals bitback see if this works. Wait. Is that right? No, that's not right. So this still needs to look like this. It's this one that doesn't. Because we'll already have it. And then similarly, structure is 101. No, so it should just be 10, and then the bitback structure, and then we close to the prime. And it makes sense that our original test passed. Next fails. Now it has 9 bits. Should have 7. But those other ones are correct. So it's just the children, it's just the structure that's incorrect. So 10. And then we add the children structure onto it. Just to double check this isn't failing in another case, right? 1353. Yeah, it's only failing in this case. Why is it a 9 rather than 11? 1, 0, 1. Why is it getting a whole extra 1, 0, 1? Oh. Okay. Right, so what if we don't do the outermost parentheses? Oh man, I have 8 minutes left. I really want to finish this in time. We're definitely not gonna have time though. It's a bummer. So what if we do, in the base case, the structure is just 0, and that the encoding is just bitback new, and then this goes away. And then in the derived case, we go, the structure is zero, 1, extend 1. And here it's 0, 0. No, it's 0, extend for children, and then we push another 0. And then in the test, this becomes just 0, this becomes just 1, and this becomes just 0, and this becomes 1, this becomes 0. So it's equals and then nothing else, and it's, yeah. Compile. Push this. Still fails. 1351 fails at the end. It's 5 and 5 now, which is good. 5 and 5 does match. And now 0, 1, 0, 0, 1 matches. And this one doesn't. So A is getting mapped to this, that matches, but equals is getting mismatched. Why is that? Why is that? This is wrong, right? It should be the encoded bit first. Get back new. Push the encoded bit on. And then it's encoding.push false for the left parenthesis. And I think this should work. I hope it works because I gotta go in 2 minutes. Hey, it passed. All right, let's call it here. Let's commit. Start building a binary symbol tree. Binary symbol nodes. All right. Well, thanks for watching. Thanks for watching, and I'll be back. I'm actually going to be back a little later today, and I think I'm just going to keep chugging at this because it's, well, I'm looking forward to seeing the outcome of it, and hopefully having it be a bunch faster. Hope this is interesting. I know it's always a little slow to watch coding, but and this was a really long stream for me, and I'm a little tired, but I do appreciate it if you stuck around this far. So thanks for watching, and like and follow and subscribe if you would. All right, thanks so much.